At first glance, Concorde's wings look like a simple and elegant sweeping triangle. But these weren't ordinary wings. They carried 100 passengers across the Atlantic at twice the speed of sound, through shockwaves and intense heat. To this day, the Concorde wing remains one of the most daring pieces of engineering in aviation history. So how do you design a wing that can take a passenger jet higher and faster than some fighter aircraft? Let's find out. The most distinctive feature of Concorde was its OG delta wings. Most airliners use swept wings with flaps, slats, and spoilers. Fighter jets sometimes use pure deltas. But Concorde's designers at Sud Aviation and British Aircraft Corporation needed something in between for a wing that could cruise at Mach 2 and still land safely on a conventional runway. The delta gave inherent strength and stability at high speeds, but the real trick was in the leading edge. Instead of a straight line, Concorde's wing had a graceful S-shaped curve, the OG. This shape generated controlled vortices as air spilled over the wing. Those vortices created extra suction-boosting lift at low speeds when Concorde had no flaps or slats to help. Engineers proved this in years of wind tunnel testing, studying vortex flow with smoke and laser visualization. Variable geometry swing wings were considered, but rejected for their weight and complexity. Concorde's fixed delta was simpler, lighter, and more reliable, and it also took advantage of vortex lift. Test pilots later described it as riding on invisible whirlwinds. At approach speeds of 160 knots, Concorde could still fly safely thanks to this effect. It was a radical idea because passenger jets weren't supposed to behave like fighters. Yet this was the only way to blend subsonic safety with supersonic efficiency. But clever shaping alone couldn't make a supersonic airliner work. The wing needed materials that could withstand the punishing heat of Mach 2. At Mach 2, Concorde's aluminum skin heated to over 127 degrees Celsius, 260 degrees Fahrenheit. Engineers initially considered titanium, which was stronger at high temperature, but rejected it. It was too costly, too heavy, and too difficult to machine for such a large aircraft. Instead, they developed a special alloy known as RR58 aluminum. This was tested exhaustively in temperature chambers, bent and stressed until failure to prove it could hold strength near its upper temperature limit. Even so, engineers knew the structure would expand. In fact, Concorde stretched up to 10 inches during flight. Pilots joked that the cockpit windshield would grow warm to the touch, which was a reminder that the entire jet was expanding around them. This expansion had curious effects. Carpets rippled, cabin fittings shifted, and tiny gaps appeared between panels. Passengers sometimes worried, but the engineers reassured them that these gaps were designed in. When Concorde cooled on the ground, everything shrank back into place. Fatigue management was critical. The repeated expansion and contraction cycle was unlike anything on subsonic jets. Engineers scheduled frequent ultrasonic inspections of the wing structure to catch microscopic cracks early. Maintenance was as much a part of the design as the alloy itself. At Mach 2, Concorde's wings were doing something else most people never realized. Beyond lift and balance, the wings carried a hidden advantage that set Concorde apart from every other jet of its time. What do you think this was? Drop your guesses in the comments below and we'll reveal it in the outro. With materials sorted, engineers started wondering how to make wings and engines work together at supersonic speed. Concorde's 4 Rolls-Royce Snecma Olympus 593 turbojets were powerful, but they couldn't run at Mach 2 on their own. The secret was in the wing engine integration. Each engine sat in a complex nacelle under the wing, with variable intakes controlled by ramps and auxiliary doors. At supersonic speeds, air slams into the aircraft too fast for engines to use. So the intake slowed the airflow from Mach 2 to subsonic before feeding it into the compressors. Sensors monitored pressure every millisecond. Hydraulic actuators moved the ramps in tiny increments, trimming the shockwave at the intake lip. Pilots could hear the system at work as a metallic hum while the ramps adjusted. If it failed, the engine could unstart, violently coughing out flames and thrust. Here's where the delta wing came in. Its shape guided shockwaves perfectly into those intakes, stabilizing them. Engineers called this wave riding. If the shockwave shifted, the engine would surge. But with the wing and intake tuned together, Concorde achieved a remarkable level of stability. The result was an aircraft that cruised at Mach 2 for hours without surging or stalling. A supersonic airliner that could reliably cross the Atlantic in under 3.5 hours. The intakes and wings gave Concorde speed, but slowing it down for landing required an entirely different approach. Concorde's wings had no conventional flaps. Instead, the trailing edge carried elevons, which were control surfaces that combined the functions of elevators and ailerons. At low speeds, the elevons drooped downward, adding camber and helping generate lift. In cruise, they trimmed the aircraft precisely, keeping it stable as fuel shifted and air thinned. The wide delta trailing edge provided the space needed for these multi-role surfaces. Each elevon was powered by redundant hydraulic systems, or 3 separate circuits, so a failure in one wouldn't compromise control. This redundancy was essential for safety at Mach 2, where even small control failures could be catastrophic. Pilots reported that Concorde felt almost fighter-like. The controls were direct with little lag. At Mach 2, even small movements translated to powerful responses. At low speed, the drooped elevons kept the jet controllable. Another trick was the drooped nose, which was not part of the wing itself, but essential for wing use. On approach, pilots needed to see the runway over that long delta. The nose hinged downward, and the transparent visor retracted, improving visibility during landing and takeoff. Form followed function in practically every sense. But even with elevons and a droop nose, the real enemy of supersonic flight was invisible. At Mach 2, Concorde had to battle wave drag. Shock waves formed along the leading edge, and if they detached, efficiency collapsed. The OG curve helped hold those shock waves in place. The thinness of the wing also mattered. At just 3% thickness-to-chord ratio, Concorde's wing was razor slim. That minimized drag, but demanded extraordinary precision in manufacturing. Panels were milled to tolerances of fractions of a millimeter. Even insect residue on the leading edge could disrupt the flow and raise drag. That's why Concorde's skin was polished to a mirror finish. It wasn't vanity, it was necessity. A smooth surface ensured predictable shock waves and minimal drag. Engineers even worried about layers of paint adding roughness and weight. The payoff was astonishing. Concorde achieved a lift-to-drag ratio of 7.5 at Mach 2, which was far better than earlier supersonic concepts, and the key to its viable transatlantic range. But Concorde's most ingenious use of its wings wasn't just aerodynamic. It was hidden inside. Concorde's delta wings doubled as giant fuel tanks. Together with fuselage tanks, they carried over 96 tons of jet fuel. But this wasn't just about storage. The fuel inside was part of Concorde's balance system. At subsonic speeds, the aircraft's center of gravity sat forward. As speed increased through Mach 1, shock waves moved lift rearward. To counter that, Concorde pumped fuel from forward tanks into aft tanks inside the wings and fuselage. At Mach 2 cruise, much of the fuel sat near the tail. Instead of trimming with control surfaces which would add drag, Concorde used fuel as ballast. 11 pumps constantly moved fuel during flight, guided by the flight engineer at his console. He watched gauges showing the levels in 13 different tanks, shifting kerosene like a liquid weight system. Passengers never saw it, but every Concorde crossing was a constant ballet of fuel, moving inside the wings to keep balance perfect. It was a perfect example of engineering turning a necessity into a solution. Then engineers worked on fuel leaks due to intense heat in the sky. On the ground, Concorde often appeared to be leaking fuel. Dark streaks ran under its wings. To many, it looked like a fault, but it was intentional. Because Concorde's aluminum expanded during flight, the tanks couldn't be sealed tight on the ground. Small gaps were left to allow for that stretch. At Mach 2, when the whole jet heated and expanded, the gaps closed and the tanks sealed. The leaks stopped at the exact moment Concorde reached supersonic cruise. Passengers sometimes asked why their luxury jet dripped fuel at the gate. Engineers explained it calmly. Only at twice the speed of sound was Concorde truly airtight. What looked like a flaw was actually proof the design was working. Maintenance crews became experts in monitoring these expansion gaps. Regular inspections ensured the deliberate imperfection never became a weakness. It was another example of Concorde's unique design philosophy of accepting quirks that subsonic airliners never faced. With these challenges mastered, Concorde's wings became more than structure. They became a symbol of daring engineering. Even after Concorde's retirement in 2003, its wing remains legendary. It proved that a civilian aircraft could use advanced aerodynamic tricks once reserved for fighters. The OG Delta influenced later supersonic studies like NASA's high-speed civil transport and today's boom supersonic overture. NASA's X-59 Quest project borrows heavily from Concorde's lessons, exploring thin airfoils and vortex lift for quieter supersonic flight. In wind tunnels today, researchers still analyze Concorde's OG curve as a benchmark. And beyond technology, the Concorde wing stands as a symbol. It wasn't the cheapest solution, it wasn't the easiest, but it worked by carrying passengers at Mach 2 for 27 years. In that time, Concorde flew 50,000 plus supersonic flights. Everyone depended on the brilliance of its wings. So what was that hidden strength of Concorde's wings? It was their sheer durability. Despite flying faster and hotter than any passenger jet before or since, Concorde's wings never suffered a single catastrophic structural failure in 27 years of service. 1943. Inside a roaring Detroit factory, sparks fly, steel clangs, and the smell of oil fills the air. Among the noise and chaos, workers are building a machine that would change the course of World War II. The Packard V1650 Merlin engine, also known as the V12, the beating heart of the P-51 Mustang, America's fastest and most feared fighter. But how was this legendary engine created? Every masterpiece needs a foundation, and for the Merlin, that foundation was its crankcase and cylinder blocks. These weren't simple car parts. They had to endure explosions inside 12 cylinders, at up to 3,000 revolutions per minute, for hours at a time. The process began with casting aluminum alloy. Workers melted the metal in huge furnaces, heating it until it glowed orange at more than 1,200 degrees Fahrenheit. Then, with a precision honed by wartime urgency, they poured the molten alloy into carefully prepared sand molds. The molds formed the rough shape of the crankcase and cylinder banks. Once cooled, these castings were broken out of the sand, cleaned, and sent to inspection. Inspectors used X-rays and gauges to find hidden cracks or bubbles. Even the tiniest imperfection could spell disaster at 25,000 feet. The war didn't allow for second chances. Raw castings were just the start. To transform them into usable parts, Packard's machinists had to remove excess metal and cut everything to exact specifications. Huge milling machines, grinders, and lathes shaped each surface to within thousandths of an inch. Coolant sprayed constantly to prevent overheating. Machinists bored out perfect cylinders, drilled oil and coolant passages, and cut bearing seats for the crankshaft. Jigs and fixtures held the block steady while micrometers checked every cut. Tolerance was measured in human hairs. If one cylinder was slightly misaligned, the entire V12 would rattle itself apart. Next came the crankshaft, the engine's spine. Forged from a single billet of high-strength steel, it was heated, hammered, and pressed into its rough shape. After forging, it went through multiple stages of machining to carve journals, counterweights, and oil passages. Balancing was critical. Workers added or removed tiny amounts of metal until the crankshaft could spin perfectly smoothly. At full throttle, imbalance could destroy an engine in minutes. Packard's attention to detail here is one reason their Merlins were so reliable. The crankshaft alone couldn't do much, rather it needed pistons and rods to translate explosions into rotation. Each piston was forged from aluminum and fitted with piston rings that sealed against the cylinder walls. Too loose and the engine would leak compression. Too tight and the friction would cause overheating. Getting this right was a delicate balance. The connecting rods, forged from steel alloy, were bolted to the crankshaft with precision bearings. These rods were like the arms of the engine, moving up and down thousands of times a minute. A single failure would mean catastrophic destruction. With pistons in place, attention turned to the cylinder heads. This is where the Merlin distinguished itself from simpler engines. Instead of side valves, it used an overhead camshaft system, which improved breathing and efficiency at high speeds. Machinists installed camshafts, valves, springs, and rocker arms. Each valve had to open and close at exactly the right moment. Workers measured valve lash with feeler gauges, adjusting clearances by hand. A mistimed valve would rob power or worse, cause a collision inside the engine. If one part made the Merlin truly legendary, it was the two-stage, two-speed supercharger. At high altitudes, thin air strangles most engines. However, the Merlin's supercharger compressed incoming air, forcing it into the cylinders at high pressure. This allowed the Mustang to remain powerful even at 30,000 feet, altitudes where German fighters struggled. Building the supercharger was almost like building a second engine. Workers assembled gears, impellers, and intercoolers. The gear-driven system could switch speeds, a low gear for low altitudes and a high gear for thin air. This gave pilots smooth performance across the entire flight envelope. Of course, compressed air was useless without fuel, and that's where the Bendix-Stromberg carburetor came in. Unlike car carburetors, this design had to feed fuel reliably in combat, even when the Mustang was upside down in a dive. Engineers solved this by using a special pressure carburetor that sprayed fuel under pressure rather than relying on gravity. At Packard, technicians adjusted jets and diaphragms to ensure the perfect fuel-air ratio under every condition. This meant pilots could slam open the throttle mid-dogfight, and the engine would respond instantly. No sputter, no lag, just raw power. Well, a powerful engine generates enormous heat. Without proper cooling and lubrication, the Merlin would seize within minutes. The cooling system used a water glycol mixture pumped through channels surrounding each cylinder. This absorbed heat and carried it to radiators in the Mustang's belly. At Packard, workers installed water pumps, radiators, and coolant pipes with leak-proof seals. The oil system was equally vital. High-pressure pumps forced oil through tiny passages to bearings, pistons, and camshafts. This thin film of oil reduced friction and carried away excess heat. Every pump was bench-tested to guarantee reliability. Then came the ignition system. The Merlin used dual magnetos, self-contained electrical generators to fire its spark plugs. Each cylinder had 2 plugs, doubling redundancy. Workers tested magnetos on specialized rigs, ensuring they produced strong sparks even at simulated altitudes. Spark plugs themselves were fired under pressure chambers to mimic thin air. A single weak spark could mean lost horsepower or even total failure. The Merlin produced incredible power, but that energy had to be harnessed efficiently. Enter the propeller reduction gear. If the propeller spun at engine speed over 3,000 RPM, the tips would go supersonic, wasting energy and creating shockwaves. The reduction gear slowed the propeller to about half engine speed, keeping it efficient while still producing enormous thrust. Machinists carefully assembled the hardened steel gears, checking clearances and lubrication. Any misalignment here would destroy both engine and propeller. Beyond the main engine, dozens of accessory systems had to be installed. Pumps for fuel and oil, generators for electricity, hydraulic pumps for propeller control, and more. Each accessory was mounted on brackets around the engine, driven by gears or belts from the crankshaft. Packard built these with modularity in mind, making field maintenance easier for mechanics overseas. Now all the pieces came together. On Packard's assembly line, engines moved from station to station. One team installed the crankshaft, the next added pistons, another timed the valves. Superchargers, carburetors, pumps, and magnetos followed. Each bolt was torqued to specification. Each gasket was sealed tight. At the end of the line, gleaming 27-liter V12 engine stood ready, stamped with Packard's nameplate and serial number. No engine left untested. Every Merlin was mounted to a dynamometer test stand. Fuel, coolant, and oil were connected, and then came the moment of truth. The first ignition. Engines roared to life, shaking the test cells. Technicians measured horsepower, torque, temperatures, and even fuel flow. Engines were run at full power for hours to prove their reliability. If anything failed, the engine was torn down and rebuilt. This grueling testing ensured that when a Mustang pilot pushed the throttle forward, his engine would deliver every single time. After passing inspection, engines were drained, sealed, and packed into sturdy wooden crates. Trains carried them from Detroit to aircraft plants like North American Aviation in California, where workers mounted them into Mustang fuselages. Within weeks, an engine cast and built in Detroit might be flying over France, dueling with German Messerschmitts and Focke-Wulfs. Only now, after walking through the factory, do we reveal the engine's origins. The Merlin was originally a Rolls-Royce design developed in Britain in the late 1930s. Early P-51 Mustangs used American Allison engines, which were good at low altitude but weak above 15,000 feet. The British tried fitting their Rolls-Royce Merlin into the Mustang, and the results were astonishing. The Mustang became faster, more agile, and capable of escorting bombers deep into enemy territory. The only problem? Britain didn't have enough industrial capacity to build Merlins for both Spitfires and Mustangs. Enter Packard. In 1940, the U.S. struck a deal for Packard Motor Car Company in Detroit to build the Merlin under license. Engineers adapted British blueprints to American tooling, and soon the Packard V1650 Merlin was rolling off production lines. By the end of the war, Packard had built over 55,000 Merlins, powering Mustangs, Spitfires, Mosquitoes, and even Lancaster bombers. There you have it, the heartbeat behind America's fastest World War II fighter. Swapping in the Merlin-powered Packard V1650 transformed the Wolverine-like Mustang into a legend of the skies. If you loved geeking out about aviation history and engineering feats, hit like, subscribe, and ring that bell for more high-octane content. Until next time, keep your props turning.